Good evening, welcome to Lecture 1 of Topic 2 of Unit 4 Light Phenomena. This video will be covering the main ideas of Chapters 16.1 and 16.2 of Book 1. So make sure you're looking in the right book because there's no Chapter 16 in Book 2. Please complete this reading before class. Here are your learning intention and success criteria. Please have a quick read, pause the video and complete the KS table down the bottom right there. Okay, so having a look here, our learning intention is we want to be able to recall that properties of light can be explained using a wave model and describe something new called polarization. So things that you've got to be able to do: recall that light is not a mechanical wave, recall light properties that can be explained using the wave model, and describe polarization of light. So things we need to know: what type of wave is light if it's not mechanical? What properties of light are there to explain? And then finally, well, what is this polarization? Not much doing in this video. So, in Unit 3, Topic 3, we examined waves, and we specifically looked at mechanical waves, mostly in terms of sound. Now, our definition for mechanical waves is a wave that requires a medium. Sound, earthquakes, ocean waves, all these things take vibration to move, and so they are mechanical waves. You are hearing me right now because the speakers or the headphones you are listening with are vibrating. The vibration travels through the air, which vibrates your inner ear, and the vibration there is converted into electrical signals. But it has to go through a medium. If there's no medium, you don't hear anything. But light is not a mechanical wave because it can go through a vacuum, space. Right? And so, as we saw in the last video, 4.1.9, it's an electromagnetic wave. It's a propagation of electric and magnetic fields. Okay, so the electric field makes the magnetic field, and the magnetic field makes the electric field, and so it continues. Now, the wave model we saw earlier, the core principles back in Unit 3 are still required here. So things like we're going to need wavelength, frequency, amplitude, interference, otherwise known as superposition. Remember when two waves go over the top of each other and the result is the interference of the two. Reflection, refraction, and diffraction. So we saw all these back in videos 3.3.1 through to 3.3.3. So I'm not going to recover that because the only difference between those videos and what we need to know here is replace the word sound with light. Everything else is exactly the same. Okay, so remember it's all about Huygens principle, or however the correct pronunciation is. Go check those videos out for you to help remember about the wave model. But light has some interesting things of it. In the 1600s, they said it was made of particles. Particles was a big thing, and Newton really liked this idea. Now, they used a different word. They used corpuscles. Today, we use photons. But then waves came around, and it was kind of the new thing on the block, and everyone said, yeah, whatever, particles, pff, let's go with waves, yeah. But then we got to the 1900s, and we started understanding atomic structure better, and Bohr did a lot of work on that, and then Einstein came along with his photoelectric effect, and waves couldn't do it, okay? Because a wave has a continuous sort of nature, and these two things were very particle-like. Okay, and we'll talk about these later on when we get to the actual quantum mechanics of this topic. But for now, what we need to know is that there are a couple of things that the wave model can't explain. Here are two examples: atomic energy levels and the photoelectric effect. And so they brought back particles. They brought back light as a particle. But light as a particle can't explain interference, diffraction, or polarization, because if you have two particles interacting with each other, things happen. They don't just add together or subtract, certainly don't subtract, and they don't continue past each other. So think about, if you go back to those videos, have a look at that spotlight image I showed with two spotlights shining over the top of each other, and then the dimmer bits past it, so it shows it goes past each other. Diffraction, the bending of light or the bending of waves as they go through narrow gaps. There's great pictures in the textbook, and I've demonstrated this in class. And polarization, which is something new we're going to talk about today. So the wave model can explain some things, but couldn't explain these two things, atomic energy levels and photoelectric effect. The particle model can explain those two things and could explain a couple of things like reflection, refraction. Particles can deal with that, not a problem. But these ones, interference, diffraction, and polarization, no, it can't handle that. So this led to the development of what's called the quantum model. Now we'll deal with quantum theory a little bit later on. This is not explaining it yet. But what we need to know about the quantum model is that light has both wave and particle behavior. Both are true. It is both a wave and a particle. Some situations you're going to learn about you have to explain with waves, like we just saw on the previous slide. Some you have to explain with particles. Again, you just saw them on the previous slide. So we need to know when to do what. The good thing is it's just about explaining. The math won't really change at your level, so we don't have to worry too much about that. So let's talk about polarization. We saw refraction back when we talked about mechanical waves, and we are going to do refraction with light with a little bit more math behind it. We'll see it in a lab if you haven't seen it yet by the time you're listening to this. And we need to remember that refraction is the bending and slowing of waves as it changes medium. Okay, so if you forget that definition, go back to video 3.3, I think it is. Now, 1669, Bartholin shone light onto a mineral called calcite. Unfortunately, we don't have any of this clear, but this is his thing. And two things happened. Some of the light went through, but some of it refracted inside the mineral. So here's a ray diagram, this image on the left. We see the light comes in. Okay, there's the normal. Some of it just goes straight through, but some of it bends a little bit and then comes out, and they come out parallel. Here is what it would sort of look like if we were to look at a pencil through a piece of reasonably clear calcite. You can see this one here, oh yeah, kind of a little bit bent there, but then there's a second image created. So it's not bending the whole image like I've shown you with optical illusions. There's that classical one of the guy in the pool with his head looking disconnected from his body with a sign saying physics is fun. That's refraction, but this has both refraction and just light passing through, which is weird. Now, Huygens did develop a wave theory to explain it, but he didn't actually give it a name. Newton, though, called it polarization in the late 1700s. Now, the definition the textbook gives is that, or the syllabus gives, is polarization is a single plane of light rather than two planes. Okay, that light is reduced down to only having one plane. The way I think of it, it's like filtering light through a straight line gap, like a set of fence posts with gaps in between the fence, with the panels of the fence. Okay, think like the gate, the fence around the school. You know, you've got poles going up and down, and then there's a gap in between it. If we were to shine light where the wave goes up and down, well, it'll go through the gap. But if the wave was going left and right, it wouldn't go through the gap. One way we could see this is, say, to grab a skipping rope and one person will feed it through the gate. If we oscillate the skipping rope up and down, well, the skipping rope will move perfectly fine. But if we try to flick it backwards and forwards, the wave won't go through the gap anymore. It'll run into the fence post. Okay. Here's a great image from the textbook. Now, just be aware, this yellow wave and blue wave is not showing electric and magnetic fields. It's showing two parts of electric field. Light from like a light bulb from the sun emits light orientated in a lot of different directions. And so you can see here we've got this sort of messy light, unpolarized light, getting into a filter. You see a filter's like a fence, gaps in between the bowls, but only the yellow ones, the ones going up and down, are making it through the filter. And so the light coming off here is polarized. We see polarization happening a lot on things like wet surfaces, which is why fishermen's glasses are often polarized so that they can easier deal with the glare coming off of reflective surfaces like lakes and oceans. It helps a bit when you are driving because wet surfaces like roads will reflect polarized light, or the light polarizes when it reflects. And our sky has a lot of polarized light because the way that light interacts with molecules, they all tend to, the light that comes off these interactions tends to be orientated together and polarized, and so polarizing lenses are commonly used in photography to help with removing glare. Okay, so what we need to be able to do is describe what polarization is and explain it just referring to the idea of a transverse wave. Remember, transverse means that the wave is oscillating perpendicular to the direction of motion, or if the light goes left to right, the wave goes up and down as it goes left to right. And here we can see that as it gets to the filter, only part of it gets through. If we had another filter over here, then this wave would not get through that one if it was pointed horizontally at right angles to the other one. If the filter was only tilted a little bit, then you would get a little bit of light through. There is some very interesting stuff with lenses like this that I will show you later on when we get to the more the quantum nature of light when we deal with it in a couple of weeks. So, in this video we have learnt about the following. We have defined light as a non-mechanical wave that can travel through a vacuum. You've got to remember that vacuum bit and that it's not mechanical. We've identified some issues between wave and the particle model of light, and we've sort of hinted that, hey, there is an explanation with quantum theory, but we're going to have to get to that in depth later on. And we've defined something called polarization and explained it using waves. For your entrance to class, please complete questions 1 to 4 in Chapter 6.1 and 1 to 3 in Chapter 16.2. Check your learning PDFs. Copy your answers into the 4.2.1 space on eLearn. Thank you very much for listening, guys. Have a great evening. Bye.